Hi, and welcome to another episode of the Oxford Online Maths Club. It's great to have you with us. My name's James. I work at the University of Oxford doing admissions and teaching and stuff. I don't know why I've started doing my biography at the start of this one. It's just me on screen today, but I'm joined in chat by one of our current students who might want to say hi at some point. They are moderating chat. Today's the day that I've got extra chat moderators in. Hello to people I can see around here. So I can see Miles in chat. I saw Casey has just joined in. Hi Casey. Timmy, scrolling down a little bit, has joined in. Nice to see you as well. This is going to be Math Club. If you haven't joined us before, hey, welcome to the club. It's not always a big blank white screen, we're going to work on that. It's a casual, relaxed place where we do some maths together. Normally I do some maths on the screen, sometimes I do the maths quite badly, and sometimes there's homework. Brilliant! So we've got a chat moderator today, he's first year student Xiao, maths and computer science, so if you want to chat to our student moderator as well, then they are live in chat at the same time. Chat's moderated, so it might take a little moment for your messages to appear on screen, especially if our one student is if they're currently typing an answer to somebody else, then chat might slow down a little bit. Bear with it. There's also some serious lag in between you typing something in chat and it appearing on screen, but there we go. People are joining in. If you've got two devices, you can, I guess, be in chat at the same time as watching the live stream, but everything's going to be out of sync and it'll be really confusing. But I guess that's the only way to do it. Right, okay. Hi Kat as well. Hi to lots of anonymous people who are saying hello and stuff like that in chat. Let's start like we always do, when we remember to, with some sort of poll for how's your day today on a scale from 1 star to 5 stars. I think I've personally had about a 3-star day. It's just been so cold and I've been so tired for so much of the week. People are voting at the moment for how their day was. Let's do the coming up as well. Coming up today on the Oxford Online Maths Club, so far every episode has started by saying coming up triangles. This time, coming up pentagons. I want to show you some facts about pentagons. They were mentioned in passing last week, and then I went away and I thought about it and I thought there's just so much nice stuff to say about pentagons that we should talk about that on the stream. Let's show you the results so that actually people can see. There we go. All the voting. There you go. There's bar charts. After the pentagons, circles. I feel like we should talk about circles a little bit again. You usually do talk about circles at some point, I suppose. There's been a bit of a geometry theme, I suppose. That's accidental. And then, further reading is posted on Friday on the website it's just been cut off, maths.ox.ac.uk/r/club. Can I make chat slightly less wide? Can I only make it less wide on that side? So further reading gets posted to the website on Friday. I put this slide up to force myself to go and type up some further reading. It's extra notes based on whatever we've talked about on the live stream. Anything we chat about sometimes inspires us to go and do something else. Coming up today, there's one vote in chat behind the poll, one vote in chat for just quadrilaterals. And one person says their day was trash. They voted for 1 star, I think. Sorry that you're having a bad day. I don't know if pentagons is the right way to cheer anybody up in this world, but we're going to give it a go. Okay. There's always the pep talk, right? There's always, can we cheer somebody up just by talking about pentagons? Let's find out. Kai's here. Hi Kai. Sometimes at the start of these I've reviewed some emails that people have sent me from last week. I've got really behind with my emails, so if you've emailed me in the last week, I might have read it, I might not have read it. There's an email address at the bottom of the screen. Right, good. Okay, I think that's all our admin. We've got further reading posted on the website. That exists for last week's episode now. Hooray. Maybe for pentagons as well. Let's find out. Right, okay, let's get rid of that and put a pentagon on the screen. Okay, here's a pentagon. I think pentagons get overlooked a little bit because squares are very nice. You can tile the space with squares. Hexagons are really nice. They tessellate as well. You can tessellate space with hexagons. In between there's the kind of problem child of pentagons that they don't tessellate nicely. Well, regular pentagons don't. Yeah, Kai's been super ghosted. Sorry, Kai. Your probability of getting a response is also, well, I do respond to emails eventually. Let's say we've got a regular pentagon with side length 1. Now, for a square, one of the things we do is we sort of join up the corners and talk about how the diagonal length of a square, that's the very interesting number square root of 2. And for a hexagon, you could do something similar to sort of split up a hexagon into lots of little parts like this, and then talk about all of these lengths as well, and draw in some sort of triangles and other stuff going on inside there. For pentagons, there's a rather nice calculation that you can do that I want to show you. And Arjun says thanks to Miles in chat. And Miles in chat recommended a video, and then it got put in the further reading, and then somebody else watched it. So that's an example of, look, maths club. That's what we want, right? Somebody turned up to a maths club with an idea for a video to recommend, and then somebody else watched it. That's what we like. Okay, so let's try and draw some diagonals in a pentagon. If I draw diagonals in a pentagon, maybe this is weird. There's only actually one length of diagonal. There's lots of choices I can make about which corners I join up, but there's only one length. They turn out to be the same length as each other. That's maybe a little bit weird. With the hexagon, there's different cases for whether you join opposite corners or whether you join nearby corners. With the square, there's just one. And somehow for the pentagon, all these diagonals have the same length. So this was me sort of skipping one corner for a diagonal, and this was me skipping two corners, but that's sort of the same thing, because if I skip two corners on this side to draw my diagonal, I'm skipping one corner on the other side. Oh, catch and watch Miles' video. Brilliant. Miles is going to steal my job at some point, I think. This will be just the Miles live stream, or Miles' video recommendations. There's quite a nice picture already, I think, because it's got these diagonals that I guess conceptually maybe they could have been different, but they're not. They're the same length. I'm going to call that length x. And I guess a challenge is to find the value of x. And because it's after 5 o'clock and I'm a bit tired, I'm going to try and do this in the laziest way I can. I'm going to try and be really lazy. Probably some of you are very great at trigonometry and angle chasing, and you can draw in lots of angles, and you can go and hit it with lots of trigonometry and apply different like cosine identities or something. I'm going to try and do this in a chill way. Okay. Mature applications. So because you've joined in, hi. If you're a mature applicant and you're applying post-qualifications, we tend to look at the most recent 3 years of what's been going on. There's more advice if you search for Oxford mature applicants on our website. Mature is just our word for anybody who would be over 21 at the start of the course. Okay. Bit of trig, yeah. Miles wants to do a bit of trig. I'm going to try and be chill about this. So I do want to mark some angles in. I'm a bit lazy about actually solving what the angles are. So there's this angle, right? For the angle in a pentagon. Does anybody know the angle in a pentagon? There's a way to work it out by thinking about walking around the edge of the pentagon and making lots of turns. Maybe chat will let me know. There's one of them over here as well, and I guess a couple down here and one at the top. I'm gonna let chat reach some sort of consensus. Cat thinks 108. Anonymous person 108. Yeah, some votes for 108. I guess the logic there, I can't remember when I learned this, probably like before 6th form or whatever, but it helps to have a way to remember it, right? That you turn 5 times, so you turn like 1/5 of 360 degrees, 1/5 of 360 degrees to 72. So I guess this is 108, or something. But I'm lazy, so I'm not going to use that. Yeah, 540 over 5. Somebody knows the sum of the interior angles. Right, cool. I've decided that I learned this way before 6th form. This is something that we know, right? I don't know. Apparently some of us are not in 6th form, but that's all right. Okay. Okay, so we've got an angle inside here. Slightly harder question then, or maybe not, since you're great at angles. What's this angle up here? So you've convinced me that this one is 108, which I'm going to call alpha. Because I'm too lazy to write 108 multiple times. And this one up here I'm going to say is beta. That angle up there. Now, chasing these angles around might be helpful if we're going to do some trigonometry. In a moment I'm going to be too lazy to actually do the trigonometry method. I'm going to try and show you something slightly different. Chat's voting. Look at all these 36s. Brilliant stuff. This is really pushing Sishao, moderating chat. Thank you, Sishao, who's frantically approving anonymous people saying 36 all at once. I don't actually know if you're watching the live stream as well. If you're not, then you've just had to approve a load of 36s. Okay, brilliant. And an equation, a kind of reason as well. Angles in a triangle add up to 180 degrees. That's pretty nice. What about this angle here? Working my way through the Greek alphabet, alpha, beta, gamma. This is a fun geometry challenge now, isn't it? I did give you a link. Okay, so I've got this angle beta up here, which is in, I guess people notice this is an isosceles triangle because it's a regular pentagon. I've got this one. And I can't tell whether people are saying 36 from before or 36. Yeah, 108 take away 72. Yeah, so people have got different approaches, I suppose, but maybe they're thinking about how this is also beta. This angle gamma is also 36 degrees. Somebody's in year 7. Hello. You're learning about angle chasing. We're chasing some angles around the diagram to work out what all these angles are in this picture. I think it's also 36 degrees, which is a bit suspicious. Hey Demi, 36. Yeah, 36 as well. Good, right, okay. So I've got you to tell me the numbers because, hey, interaction is good. It's nice for me to know there are people out there. There's actually a nice way to spot that beta and gamma were going to be equal to each other. For this pentagon, and the reason I want to bring it up is that it's you can use it on other regular polygons as well. Not quite in the same situation, but there are other cases you could do for regular polygons where you might use this trick as well. Let me show you a quick diagram to show you what I mean. So I'm going to try and prove that beta and gamma are the same angle. Without using the fact that they're both 36. I know that sounds stupid. Like, you just told me, everyone in chat just told me that they're both 36. But there's a nice reason why this is this corner is split into 3 equally by these lines and diagonals. Conceptually, it doesn't have to be. When you split things in thirds, they don't have to be split equally, but they are. Beta is equal to gamma. Here's how I know. So here's another picture of a pentagon, and I've marked in a few different diagonals, and I've also drawn a circle. I promised pentagons and circles today, and I think this is the angle that we were calling gamma, and this is the angle that we were calling beta. I think it was that way around. Yes, gamma for the pointy shard one, and beta for the angle in the side triangle thing. Now, I'm going to throw this to the chat as well. So I've drawn a circle and chat's already shouting circle theorems at me, which is an exciting time to be alive. Hi Marcus, we're just finding some angles in a pentagon. So somehow, does anyone want to tell me which circle theorem we're doing? Oh yeah, okay, just hang on, there's the SOHCAHTOA right angle stuff. I don't want to miss that. Yeah, Hypotenuse, you're way ahead of me finding X. It's going to be in terms of 72 degrees, 36 degrees sort of stuff. Yeah. So there's the same segment thing. Oh gosh, is it the same as alternate angle? Can I remember what alternate angle segment is? Maybe I shouldn't do this joke, but sometimes people notice that I can't remember the alternate angle segment, the alternate angle theorem, and sometimes people think that that's information about the maths admissions test, because if I can't remember the alternate angle segment, then it can't be on the math test. But I'd just like to reassure chat that I do relearn my circle theorems each time we're about to set them out. So it really could be the alternate angle one. Oh gosh, that's the one about tangents, right? Oh, it feels like a test. Okay. I like to think of it for this picture as angles on the same segment. So let's mark in that segment. So angles on the same, subtended by the same segment are the same. So if you've learnt this sort of circle theorem at GCSE or equivalent, then it's quite easy to only use it when you see it. When you're told to use angles on the same segment, maybe someone draws in the circle and draws in the the segment for you and asks you whether things are equal. But somehow there's this more advanced skill that you could maybe work on, especially if you're post GCSE. If you've done your GCSEs or equivalent and you're moving on into other harder maths, you could maybe go back and look at those skills that you have from before and try and learn this kind of harder skill of spotting when to draw in a circle and when to use all your circle theorems that you know. You've kind of got this for free. Yeah, that was a terrible line, wasn't it? That was one of the worst things I've ever done. I'll have another go just for you. I'm trying to use an actual Miro. Oh no, this is even worse. Type. Why would type not default to straight line? There we go. Same segment on the bottom. There we go. Okay. So this is my lazy approach to realise that for a pentagon, there's something really nice going on, that the diagonals trisect the angle at the top. That's a little bit unusual. You can't always trisect an angle using rulers and compasses, but here's an example where we've successfully trisected an angle. Okay. So, which we could interpret as some sort of circle theorem, that the angle, these triangles kind of have the same base and then they're on the same circle, so they have the same angle at the top, which is half the angle at the centre. And the angle at the centre is 1/5 of a circle, so that's 1/10 of a circle, which is 36 degrees. Right, okay. So without chasing any triangle facts, you can work out the angle. Right, where am I going with this? I would like to find x, I think. I could do the thing in chat. I don't know about every pentagon, Casey. I'm only talking about regular pentagons today. And in fact, it is not true that every pentagon can be circumscribed by a circle. Some pentagons, the corners are in the wrong places. How do I know that angle is beta? Oh, this one over here, I guess I know it's the same thing as this angle up here by symmetry. That was the one I called beta before, and this one's beta. And I know that beta and gamma are the same because of this brilliant circle fact, that you can move this point around and the angle stays the same. If you haven't seen that before, it's an amazing circle fact about angles and circles. Yeah, okay, right, good. Regular pentagons, you can put a circle around them. Other regular shapes are available. Homework, if you find that neat, then homework is, I guess, to think about one of the other unloved shapes, like a 7-sided heptagon or a 9-sided nonagon or something. And one of the other unloved shapes, draw in some of its diagonals and see if there's anything nice going on. See how many different sort of lines you get, and maybe try and solve some of the edges when we get there. Okay. Oh, matrices. Why are matrices in chat? Ooh, okay. So I think we want to find x, and someone very clever in chat told me that I could just drop a perpendicular and think about using SOHCAHTOA, right angle triangle stuff. I'm actually too lazy for that, but I do know the cosine rule. So I'd like to show you an approach to find x using the cosine rule. We should maybe do a bit of a straw poll in chat. Let's try and do a straw poll to find out how successful this next 5 minutes of my life is going to be. It's going to be, the question is really cosine rule, and the two options are yes, I know what that is, or no, I don't know what that is. Just to find out how, I want to use the cosine rule next. And I also want to try and pretend that that's the lazy thing to do. Let's do the non-lazy thing. What chat's voting? The non-lazy thing would be something like drop this perpendicular, divide alpha by 2, so that's like 54 degrees. And the non-lazy thing with them is marking this square right, marking this right angle. It's like, oh my goodness, there's a cosine adjacent, sine 54 or something. Oh my goodness, and don't forget to double it, so it's like 2 times sine 54 degrees, which is sort of it's sort of a very precise answer, but also not very illuminating, because I don't know what the value of sine 54 degrees is. I could maybe go and grab a calculator and work out the value of sine 54 by typing into my calculator, but how does my calculator know the value of sine 54? And also doesn't feel very satisfying, doesn't feel very mathematician. So it's sort of, what you would do in school maybe. Cosine rule has got lots of votes in chat. Just a quick refresher for the 11% of people, and I am thinking a little bit about a couple of people who said they were in year 7, who a couple of people who said they were in year 7. Let's do the cosine rule really quickly, but I'm going to do it on a particular triangle, so that'll be nice. Cosine rule works like this. It's a relationship between the angles in a triangle and the side lengths. The general rule works like this. If you see a triangle, then a squared is equal to b squared plus c squared minus 2bc cosine of alpha. Well, alpha's that angle at the top. That's an a. That's the cosine rule. Hey, if you're in year 7, you just learnt the cosine rule 5 years early, 4 years early or something, goodness knows. It's a little bit like Pythagoras. That bit looks like Pythagoras, except there's a little correction on the end to allow for the fact that if alpha's not a right angle, then the other side's not quite the length you would expect for a right angle triangle. Okay, I'm going to call this lazy because, so you don't... I'm not going to prove it for the year 7s or for you, Kai. We're kind of quote it because we're feeling lazy. I'm using the word lazy quite a lot, and that's because I'm going to find x without finding alpha, and without finding this sort of thing in terms of sine weird numbers, which is going to give us a much more satisfying answer. So by keeping some variables in, being a little bit lazy and not subbing in the values that we know, and being lazy and keeping them as variables, we're going to end up at a much more satisfying answer. Promise. Right, okay, watch this. Let's take that triangle for an example of the cosine rule. Hi year 7s, again, you're not learning this for the next few years, but so here, as an example, the side lengths are now called 1, 1 and x, and the rule is the opposite side is 1 squared plus 1 squared minus 2 times 1 times 1 times cosine alpha. 1 plus 1 is 2, welcome to the Oxford Online Maths Club. So this is x squared is 2 minus 2 cos alpha. What have I done wrong? Have I done anything wrong? Panic. Calm. Yeah, I don't know what I'm doing. No, I'm good. What have I done? Chat, help. Am I good? I think I'm good. Yeah, it's probably fine. Oh, sine 54 degrees is the same thing as cos 36 degrees. Do I know cos 36 degrees? I'm not sure I do. So that's a bit of a shame. But yeah, I think you're right. I think that is true. Yep, okay. I'm happy so far. X squared is 2 minus 2 times cosine alpha. My bit of paper's wrong. I'm gonna roll with just true maths. People will tell me. Oh yeah, brilliant. Oh, okay. Separate conversation going on at the same time. Ah, I know what I've done. This is true. This is a good example of the cosine rule. I am silly. Right, okay. Yeah, it looks right, looks true. It's not the equation I was expecting to write down because I've mixed up my notation on my bit of paper. It's a live maths stream, anything could happen. Maybe even correct maths, who knows? Okay, my plan is to use the cosine rule without solving for the value of beta. This is a good example for the year 7s. Here's a nice fact that relates together the side we're looking for and cos alpha. So if you're willing to write down alpha as 108 degrees, then hey, you got down to an answer. It's not a very useful answer because who knows what the value of cosine 108 degrees is, but hey, there's an answer. We seem to be finding quite a lot of answers. We've got this one in terms of sine 54, we've got this one in terms of cos 108. Oh my goodness, who knows what's going on. Let's look at some other triangles. I can get this, I promise. This is one a rare maths club where I practiced in advance beforehand, and it's doesn't seem to have worked, does it? Here's another triangle that we could look at. For this triangle, 1 squared is equal to 2x squared minus 2x squared cosine of beta, and I am not proposing that we solve for beta. Instead, I'd like to look at that triangle again on the side, but I'd like to look at it the other way round. To focus on the angle beta. Now, year 7s, I know I just told you the cosine rule using alphas over here. It's actually true if you switch your Greek letters around, so long as you remember to use the side opposite the angle as your opposite side thing. So this one is going to tell me that 1 is equal to The opposite side squared is equal to x squared plus 1 squared minus 2 times 1 times x times cosine beta. Now, this is why I'm calling this method lazy, because you and I sort of both know that beta is 36 degrees. We can go and solve one of these equations to get x in terms of cosine 36 degrees. We don't really know what cosine 36 degrees is, so bit annoying. Here's what I'm going to do. I'm going to eliminate cosine beta from these equations. This one over here, there's a 1 on both sides, so I can get rid of that. So this one says that x squared minus 2 times x times cosine beta is equal to 0. So either x is equal to 0, which is clearly nonsense, or x is equal to 2 times cosine beta. That's pretty good because, I mean, it's related together two of the things I don't know, x, which I want, and beta, which I don't really care about. And what I can now do is take this and use it to eliminate cosine beta over here. So over here, I've got a cosine beta. I don't really care about beta. I just want to find x. I'm being lazy. I don't want to solve about beta along the way. I just want to know about x. So I'm going to write this equation out again, but I'm going to replace. So this said that x was equal to 2 times cosine beta. So when I see this 2 times cosine beta here, that's an x, and I've also got another x squared. Let's not forget the x squared in the middle. So that's 2x squared minus x cubed. And now I've got an amazing equation to go and solve that doesn't involve any angles, doesn't involve any trig functions, no cosines or sines, no 54 degrees, no 36 degrees. I've just got a fact about x on its own. This is good because it's now a polynomial. And one of my favourite things to do is to convert geometry problems into algebra polynomial questions. Okay. Ooh, right, okay. First time catching a live stream. Hi, welcome to the live stream. This one looks quite messy. I'm working in this direction. Anyway, got an equation. This is the sort of thing where every individual step is not that bad, and then I hit an equation like this, and I reckon people in chat probably want me to say where the equation came from. Is anybody going to post in chat? I'm confused. Yeah. Good, right, good. Okay. 1 minute summary of what's happened so far. We used some circle theorems from GCSE to decide that some angles in a pentagon are brilliantly, they're the same value. Too lazy to work out what the value is right now. But this angle here, gamma, and this angle beta, they're actually the same because of some circle theorems from GCSE. That meant that I could draw these two separate triangles, and they've got the same angle, and lots of the sides in common. They're different triangles, but they use the same variables, x, and beta, and the number 1. So because you learn loads of triangle facts at GCSE as well, you can write down these cosine rule statements. There are different equations involving x and 1 and beta, and now I'm solving the equations. And we're really good at solving equations. So here goes. Okay. Yeah, instead of typing numbers in, this is the great summary. Instead of typing numbers into my calculator, I solved a cubic because I'm lazy. Yes, that is that is the summary of today's episode. In my head, that made perfect sense for an episode of what we were going to do today. Lazily solve a cubic equation. It's not a bad cubic equation, it's a nice cubic equation. When you see a cubic equation, you might want to try and factorise it, which is exactly what we're going to do. Spotting a factor, it's not always possible, but this one's actually being very nice to us because I can see a root. I can see a root, a number that works in this polynomial. I wonder if chat can see them too. Factoring things out. Oh, this is an awkward bit of audience interaction because if nobody wants this. Oh, factor theorem! Yeah! Oh, area of the shape. Miles is proving the cosine rule in chat. Thank you. If you've just learnt the cosine rule, there is a proof of it over there. Yeah, what? Brilliant. Okay, people saw that. Yeah, people saw that if you plug 1 in. Oh, brilliant. Phew. And if I factorise this out, I think I get this. And x is not 1. 1's the side length of the pentagon. X is clearly bigger than 1. So x satisfies this equation over here. And now we've got a quadratic equation. And I think year 7's included, or maybe not year 7's included. When did you learn about quadratics? This is really testing my knowledge of the UK school system. At some point you learn how to solve these quadratic equations using some sort of quadratic formula. And the solution to this one turns out to be 1 plus or minus root 5 over 2. Oh, but wait. Wait, x is definitely positive. Along the way here, I've used the fact that x is non-zero, x is not 1, x is positive. It's sort of funny that the maths doesn't remember along the way. I already said, anyway. That's a nice final answer. Because that's a number with a nice name. Quadratics might be year 8 content. Okay, year 7 is you can look forward to triangles, circle theorems, solving cubic equations, quadratic equations, golden ratio at the end. So somehow hiding inside a pentagon, there's this fact that this diagonal is 1 plus root 5 over 2, which I really like. I just think it's neat. If you draw a 5-pointed star like this, then the side length of the star is golden ratio times as long as the side. Golden ratio is sometimes rather cryptically given the symbol phi, Greek letter phi, which is a little bit odd. Golden ratios here. So some people will have other ways of writing this, of course, because if you went straight in with your trigonometry, then you'll have got this kind of 2 sine 54 degrees. And I now bring you the great consequence that sine 54 degrees therefore must be 1 plus root 5 over 4, because these answers have got to agree. So I think I started this not knowing the value of sine 54 degrees, because that's crazy. But it's got to be this to make your trigonometry methods drop a perpendicular. Someone in chat said this. Drop a perpendicular, use SOHCAHTOA stuff. 2 times sine 54. Okay, it's going to be 1 plus root 5 over 4, so that it agrees with this nice golden ratio answer. I reckon some people in chat have maybe seen golden ratios in Pentagon before. If you haven't, this is a fun thing to play with. The story doesn't end there. Another question you might, I guess, reasonably ask is, instead of finding the length of the diagonal, let's try and find the length to the middle. So let's try and find the length from the centre of the pentagon to one of the sides. Now you can do this with trigonometry again, chasing angles around and writing down facts about cosines. It's actually a lot better now that we know that sine of 54 degrees has got this nice value. You can use that, if you like, in your mission to find like the value of y. Or you can try and do some equations, and it turns out that that length also has there's a nice equation that has some nice solutions. Can every sine, can sine of every angle be written in surd form? No. Lots of them are really bad. And it's actually, I guess, an interesting question. Which values have a reasonably nice sign on the right-hand side that you could express with just addition, multiplication, division, and square roots, or nth roots, I suppose I'll allow. And most of them you can't, but some of them you can. Just arrived and seen this mess. It's not a mess. You just got to read it. You got to read it in. You got to read it in this order, and then it makes perfect sense. So the question was, given a pentagon, drawing the diagonals. All the diagonals are the same length for a pentagon. How long are they in terms of the side length? And we thought about doing this by angle chasing and doing some geometry, but there's actually a nice way where you write down some equations instead. That is my pentagon geometry. By the way, because sine 54 degrees is nice, and because this length x is nice, that means that there's a nice way to draw a pentagon, if you have to, in some sort of situation. Let's work it out. So it's enough if I can construct a triangle that has side lengths 1, 1, and 1 plus root 5 over 2, then I can kind of piece those together. I think I can build those and overlap them to build a pentagon. I've got the right angle for the corner. Yeah, I was going to not use the word transcendental. Yeah, so there's a good question in chat. Before I do this construction, which is going to be even weirder. Maths Club started out aimed at ages 16 to 18, but we're on the internet, and everyone's here, right? Well, lots of people are here, so people older or younger are also welcome. The formula we use for this is if your age plus your enthusiasm is between 16 and 18, then you can probably learn something from here. If you're older than 18 and enthusiastic to a non-zero amount, then you could probably learn something here as well. Okay, yeah, pentagons and golden ratios, really good fun. We're going to try and construct it now, which is going to be a little bit awkward. So in order to draw a pentagon, only using, this is a classic Greek thing, only using rulers and compasses, also straight edge and compass, all we need to do is make this triangle. So if I have a starting unit length, I just need to make something that's 1 plus root 5 over 2. So I'm going to show you a recipe for finding a line that's of length root 5. Works like this. Draw some axes, which is possible because you can do right angles using compasses and straight edges. Draw a bit of a line, perpendicular bisect, extend that. Hey, you've got some axes. Extend those lines out. And using your unit length that you started with, mark out along this axis a distance of 1, and mark out a distance along this axis of 2, which you can do by, you don't have a ruler, but you do have this set length. You can set your compasses to the length of this set length, count it out 1, and then count out 2 along there. And 1 plus 1 is 2, as we've already covered on the Oxford Online Maths Club. If you do that, then you can get your straight edge and you can construct this line that goes through those 2 points. If you do that, then the bit you get out at the end, it's got length root 5. Okay, so my steps are something like, this is for people who like, the classic geometry of drawing things with straight edges and compasses. Draw some axes, mark in the points 2, 0 and 0, 1, which you can do by counting, put in the hypotenuse, and that is square root 5. Okay, I'm not quite done, because I need to add 1 and then divide by 2. So to add 1, draw a circle around this point of radius 1, which you can do because you set your compasses to 1 and then you draw a circle around 0, 1. And find where it intersects that line, and that's how you're going to add on 1. So you've got root 5 on one side, you've got 1 on the other side, and that gives you root 5 plus 1, and then bisect the line to get 1 plus root 5 over 2. And this is a sort of recipe to get a line of length 1 plus root 5 over 2. And then finally draw that line in the sand. Get your compasses out one last time, set them equal to your unit length that you started with, mark off 2 circles around the edges, building this isosceles triangle. Where those circles cross gives you that point of intersection at the top. This perfect triangle. Perfect triangle? Am I going to call it the perfect triangle? Sometimes people get very emotional about the golden ratio, right? They say perfect rectangle. I don't know. Right, good. Okay, we've managed to make a triangle. Kai's forgotten what we were trying to do. Age minus 11 plus enthusiasm minus 18. Haha, right, good. I just think it's nice that you can make a length of root 5 using rulers and compass and straight edge. And that's how you might build this. This gives you a series of instructions for how you might construct this angle at the top, which, if I'm not being lazy, then that angle at the top was 108 degrees. This is then a good way to get. So what's that last step there? Draw the 1 plus root 5 over 2 triangle. And that's amazing, we get this 108 degree angle. Is it 108 degrees? Yes. Yes, it is. That's how you get a 108 degree angle. This is good if you want to draw the Maths Club logo. That's right, we have a logo. the first step is to construct 108 degrees, and that's the angle in the Maths Club logo. The Maths Club logo looks a bit like this, and there's an angle of 108 degrees in there. The Maths Club logo is drawn. That's a terrible picture of the Maths Club logo. Check the website for a better version of the Maths Club web logo. Let's try and load it up now. Can we get this on screen? So the logo for a Maths Club uses the angle from a pentagon to look. Oh, I've even drawn it the wrong way around. Okay. The logo for the Maths Club uses the angle in a pentagon, 108 degrees, because it's drawn on a Penrose tile. A Penrose tile is one of two tiles that are used to tile the plane aperiodically. So it turns out there was a role for pentagons and tiling eventually. In the end, the thing to look up is Penrose tiles. That is a shocking picture of a logo that I was actually quite pleased with. The logo looks like cheese. Can I put that on the website? It's a rhombus. It's got all four sides the same length. Yeah, you're right. I've trapeziumed it. The wrong way. Where'd you put the letters? Yeah. Cat's not wrong. Somebody once wrote to me to ask if they could put the logo on a t-shirt, and I thought that was a terrible idea. But if they're watching, then here's your step-by-step guide for how to design your own off-brand merchandise. What's the other one that it tiles with? It's very narrow tile. Can I remember the angles in the other tile? Oh my goodness, it's another rhombus with different angles. I think 36 degrees instead of 72. And there are rules about how you tile with them. I encourage people to look up Penrose tiles. There are different formulations of them as well. There's one that uses two rhombuses that I always think of because it tiles outside the front of our office. The maths building has got these Penrose tiles out the front, but there are other ways of building these Penrose tiles. Okay, wasn't really planning to talk about Penrose tiles, so I'm going to be really vague, even more vague than normal. This bit's fun. We got questions? Questions about this? What questions about Maths Institute, if you like? Yeah, cool display. We've got the Penrose tiles. We've also got an art exhibition going on at the moment. If you're in Oxford, 36 degrees is correct. Thanks Wikipedia and thanks Miles. Previous question: how do I work out y? That is a question that's also my question. I kind of suggested this would be homework, but let's have a quick chat. So for y, I'd maybe draw in some more lines that are also y. I'd maybe think about this angle up here, and I'd maybe hit things with the cosine rule. Hitting things with the cosine rule is sometimes the best way to get into things, I suppose. So this angle here, in particular, is interesting to me because it's a circle theorem thing, right? Circle theorem for the angle at the centre. So then you've got an angle in here, and then you've got some trigonometry, and you've got maybe you hit it with some trigonometry at that point. I don't know. Circle theorems, yeah. Circle theorems because angles at the centre. Once you've drawn in these two lines, then you'll maybe think about angle at the centre. And then once you've marked that in as what it is, then dropping the perpendicular seems like a good thing to do. Just really like the idea of dropping the perpendicular. Here we go again. Yeah, no, okay, right, we're backing out. So this is maybe going into further reading, but something you might be interested in, I suppose, is I put loads of work and time into showing you how to draw root 5. Was that stupid? Is there a better way of making root 5? And if you needed like root 6 or something, what would you do? Could you use your compass and straight edge to make me a root 6? You need it for a project. You need 2 points there, root 6 part. How do you construct that? Maybe there's a better method, right? Like I did this really quite 1 and then 2 angle, add them up again. Yeah. Ooh. Kai says, now you know how to draw the pentagon. Just draw it. Go and measure it, which I think is fine with me. That's the kind of experimental approach to, now that we know exactly where pentagons are, I'll just go and make myself one and then we'll measure it. So root 5's in here from counting out. Maybe a question to make a triangle with hypotenuse 10 and side 8. Ooh, another axis, sort of 5 on one axis, 1 on the other axis. That makes square root 6. I'm worried that that's square root 5. Oh, that does sound clever. Oh, that does sound clever. Square root 5. Now that we know how to make square root 5, put that on one axis. Put one. That is not what I was thinking of, but that does work, doesn't it? Oh, I love it. Put a square root 5 on one axis, put 1 on the other, add them up, square root 6. Absolutely brilliant. I love it. And I also love the way that this kind of demonstrates not just how to make square root 6, but as soon as you see this, you've probably got an idea for square root 7. Who was that? Was it an anonymous person in chat? Yeah, just an anonymous person, no thumbs ups. Yeah, that was brilliant. And they got auto-corrected, so I think they're on mobile. If you're watching on mobile and you just type sort 5 on one axis, 1 on other axis. Very good. That reminds me of the there's this spirally shape you can draw. I'll put a proper picture in the further reading, but just to... I shouldn't promise too much for the further reading. Something... how does this work? So you can do something like this, where you have you start with an isosceles triangle, and then you put another 1 on this side to make square root of 3, and then you put another 1 on this side to make square root of 4, aka 2, and then you put another 1 on, and you keep putting 1s on and joining things into the origin, and you get square root 4, square root 5, spiraling around a little bit like a seashell or something, maybe. Is it called an Archimedes spiral? Yeah. This is really brilliant. Okay, how to generate other square roots. And I guess you know how to make... yeah, so we can maybe run into trouble if we want to... No, we can add things together. This is brilliant. Cool. Maybe I don't need to tell people about Carlisle cycles. Guy says, what was your method? And I've just decided that it's not really worth it. I guess it links us back to algebra again, so I'm going to tell you this other method, but to be honest, this is pretty good. I guess this is a lot of effort if you need to make root 37 in a hurry. Oh no, you'd start at 6. Ooh. Anyway, a different method that approaches this in a slightly different way is to construct, and I really don't know how anyone could be good enough at geometry to think of this, but maybe that's just because I'm not very good at geometry. If you construct a circle with one point at a 0, 1 and the other point at SP, where these are maybe whole numbers, so that means to do your counting along to find S and count upwards to find P, doing this sort of grid stuff to make sure everything's square and using lots of right angles. If you draw a circle that has that as its diameter, which again with compass and straight edge means something like find the middle and then set your compasses to be half from the middle to one of the points, draw a circle in. That is not a good circle. We're going to use the circle tool. Oh my goodness. Make it good. There we go. Oh, how do you make things good? It's the button for competence. I know I do need to cheat. There we go. Okay. Then the roots you get out, the points where it meets the x-axis, they are the roots of the equation. Oh my goodness. X squared minus sx plus p equals 0. So the sequencing here is something like, if you want to solve an equation like this quadratic, so maybe you desperately want to solve the equation x squared minus x plus 1 equals 0, then what you do is you mark in the point 0, 1, the point SP, you draw that circle, and the points where it meets the axis are the roots of that equation. So it's sort of almost a kind of graphical way of solving quadratic equations. If you have some sort of magical expanding circle and you're willing to count along grid squares, then you plonk your circle down over those 2 points, and the intersections are the roots of the quadratic. This, if you know about A-level equation of a circle, this is not hard to prove. You can prove this, I believe in you, if you know the equation of a circle. Writing down the equation for this circle is the hard bit, I suppose, or is most of the work. Other than plugging in y equals 0 is the good bit of the work. Okay. Yeah, it's not brilliant. Ooh, spiral doesn't get back to the beginning. Yeah, it doesn't overlap. It does some weird stuff. After about 17, it gets all the way around, but not quite perfectly. It's a little bit disappointing after that, I think. Well, disappointing is a strong word. There'll be a better picture of that spiral in further reading. Oh my goodness. Not the best pictures today for what's turning into a geometry episode, so that's all right. People are doing maths in year 12. Yeah, we think it's, I think I checked at one point, it's about something like between 10% and 25% of schools teach maths in that order, doing maths in year 12 and then further maths in year 13. And some people cash in the A-level and do an A-level in year 12. For Oxford admissions, if that's the question, for Oxford admissions, it's fine with us. We think loads of people do this. For maths at Oxford, we would usually just count that towards the offer. So if you've already got the A star, then you've already got the A star in maths. Hey look, Kai has written out the equation of a circle. Kind of thinking about increasing the eccentricity of a parabola. Ugh. Which points come to the ellipse. Is this a criticism of my circular ellipse, or no? Good, okay. Much harder question then is which numbers can you do something like this for? So we got lucky here for the Pentagon, and we needed to solve a quadratic equation, and A, we're brilliant at solving quadratic equations, and B, there's this technique with a circle. If we really have to solve a quadratic equation, you go and do this sort of thing. This has got a name, by the way. This is called Carlisle circle. Named after someone called Carlisle. Not a criticism of my circle, just a fact about parabolas. Good, okay. Sometimes we want to solve an equation that's not a quadratic equation, and that gets hard quickly. You might have seen earlier on in today's live stream, we had a cubic equation that we needed to solve, and we sort of got a little bit lucky because we spotted a root. There is such a thing as a cubic equation, but the more terms you have in your polynomial, the kind of harder it gets to write down solutions. There's this separate problem of which numbers can you construct using just compasses and straight edge. We see all roots of quadratics. It's fine using this Carlisle circle, but what about other things, like the cube root of 2 or something? And that relates to some really classic problems. The problem of like constructing the cube root of 2 is a classic geometry puzzle about trying to double the size of a cube. If someone gives you a cube, can you use your ruler and straight edge to measure out the net of a cube that has twice the volume? To do that, you'll need to make the side length cube root of 2. And turns out that you cannot generate cube root of 2 just using ruler and straight edge, no matter how many circles and perpendicular bisectors and things you draw. Yes. Is it Cardano formula? Sort of thing that I'm going to put in the further reading. Some people, I think, learn the cubic formula. Let's not learn the cubic formula. There is such a thing as a quartic one that nobody really learns. It's too awful. So there's some of these problems. I suppose the edge that we're working towards here is that some of these problems do have a solution. There's lovely methods like this to generate. If you know how big square root 5 is, you can generate square root 6. And there's slightly weird methods that relate together algebra and geometry to try and move between those two worlds, to move between roots of equations and geometric, draw your circles using your compasses. But the edge we're working towards is that some stuff in algebra, some of the polynomials don't have nice solutions in terms of simple functions and operations. And also some geometry problems don't have nice answers in terms of rulers and straight edges and compasses. And the theory that links both of those together is called Galois theory, which is named after an amazing mathematician called Galois. And I'm really not going to teach Galois theory right now. But it's sort of amazing that these different fields of geometry and polynomials and algebra more generally, Galois had something to say about all of them all at once. It's one of the big kind of adverts for sort of studying maths at university, that lots of the things you already know about in school have secret underlying connections. That's the sort of thing that people really look forward to doing maths at university, I think. One of my big regrets is that I didn't go to the course on Galois theory when I did my maths degree. One of my plans is one day to sit down and properly learn how Galois theory actually works under the hood. Yeah, Galois got quite a tragic story overall. Very young. Somebody's done A-level maths in 4 months, and history and Latin. Wow. I wish I knew the Latin for that's amazing. Okay. Just thinking, what does maths deal with? Think about what does maths deal with? Like it's not like science. Physics deals. Okay, so philosophy question at the top of chat right now. Physics deals with real phenomenon, and chemistry deals with chemicals. I think the chemists have got opinions as well. Do they just deal with chemicals? Maybe. What does maths deal with? It's not numbers, because it's not all number theory. So some people would say that maths deals with truth, which is a very sort of all-encompassing and not very satisfying answer. The study of just anything that happens to be logically true, follow from other logically true things. Some people study the truth itself, though, and then it's a bit of a question of what are you doing at that level. I think some people would say that maths is about explaining all of the things you previously mentioned in physics and chemistry, but providing them with the tools they actually use to understand those real phenomena. That none of that's possible without using some maths. You're just not going to explain your hydrogen atom without having some level of mathematical knowledge about what's going on in there. Good. Okay. Oh, questions in as well. I did not give a good answer to that. I'm not a philosopher. Was that obvious? Yes. What are the Oxford offer holidays going to be like? It's going to vary by college. If your college has invited you to an Oxford offer holiday, I'm sure it'll be great fun. Are there any lectures more about? I think it probably more about the college, because I think it's organised by your college. It's not something I personally know about. You will, if you're in Oxford, you'll get a chance to see Oxford. You should come and have a look at our Penrose titles, if nothing else. Master's plan. Do I discriminate against people who set A-levels in October? I think an A-level is an A-level. So it's not. Oh no, the philosophy. So I've managed to annoy. Saying maths is the study of truth annoys a lot of more applied-minded mathematicians. And saying that maths is a tool for doing stuff annoys actually most mathematicians. I think I'm annoyed by both phrases somewhere. Annoyed by both of those pictures of maths I just presented. Maths explains physics, which explains chemistry, which explains biology. Yeah, I've seen that sort of chart of who's trying to explain whom, but yeah. So my favourite maths topic is fluid dynamics, which is pretty close on the physics end of maths and physics. We try to do physics problems using mathematics, using differential equations, and asymptotic analysis. But I shouldn't just say nouns. Yeah, should we do some computer science at some point? Should probably have some computer science. Does Oxford now tend to favour state school students? I think that most people in the UK are in state schools, not in private schools. People at private schools are still overrepresented in Oxford. Not by as much as people might guess, but there's still more proportion of people at private schools. Sorry, more more of our students are from private schools than it is true of the 18-year-olds in the country. The numbers are going in a direction that I don't think is an unfair direction. I started a shout out for Landau and Lifshitz. I had that book as an undergraduate. It's extraordinarily difficult, really hard. If you think I'm bad at explaining, no, I shouldn't attack. That's on finishing Trinity College in a couple of weeks. I hope you get to see the maths department. Every definition of maths is annoying. It's too complicated, and it'll annoy each other. At interview for math and philosophy, yes, you get asked about both sorts of subjects. Asked about maths questions, and you might get asked philosophy questions. Jamie wants to know about the contents of the Oxford Maths degree. Jamie, we made it all kind of open source. Not the lectures, but the course materials are just on the course. There's a course website. If you go to courses.maths.oxford.uk, you can just access all of our materials. So if you want to learn about introductory calculus, then it's just there. There's a PDF of lecture notes and stuff, and you can see quite precisely, you can see what the mix of applied and pure mathematics is. We do a bit of both, and people get to choose. Next week, you can look forward to actually having a student on the stream. I am trying really hard to set up having students on the stream, and we're going to talk about something completely different. Probably not triangles. We'll see. Maybe triangles are this season's big thing. But you know, take care, everyone. Have a great evening. Have a great week. We will see you again in 167 hours for another episode of the Oxford Online Maths Club. Thank you to Sishao in chat, answering questions and approving chat messages like a hero for the last hour. And thanks to people behind the scenes who make this actually happen. Right, good. How do I switch it off? People behind the scenes who make things happen. Yeah, sign up. There we go. People behind the scenes, help. No, we got it. We found the button. I've done more than 100 of these. Why am I so bad at that bit?